On this episode of Dirty Elbows Garage, we are back to working on the small engine dyno. We're putting in a ton of upgrades, but we're also taking the DIY part of it and making it a lot more DIY for those of you that want to make one yourself. Let's get into it. Okay, let's cover those upgrades. So first and foremost, this dyno did great. The goal was to spend as little money as possible, build it to measure torque and RPM of the engine as I remove the governor, as I play with my fuel jetting, things like that. It did a fantastic job. But being cheap as possible came with some compromises. The first one being the hydraulic reservoir. Instead of a steel reservoir, I used a bucket, and the bucket cracked over time. I kind of expected that, but the idea again was to get away with what I could do as cheap as possible. So that's the first thing I'm going to upgrade. The second thing that I'm going to upgrade is these two things being separate weldments. The engine was sitting on its own weldment, and then the load system was on its own weldment. That means its mounting base was part of the load path when the chain would tighten up and the engine was under load. And the problem there was that there was a lot of flexing in the table. Even after I reinforced it, it could be better, or it should be better than it was. So that's the next thing I've addressed. And then finally, and this kind of relates to me making the design something that people can use, is that with the original design, I only put about 15% of the design work into SolidWorks. And I did that for the DXS, for the length of the tube. The other 85% of what needed to happen was all up here. So what I had to do with the next version is I made sure to get every nut, every bolt, drawings, bill of materials, so that all the information relating to this dyno is in that CAD package. Let's jump into SolidWorks and look at that new design. Welcome to Small Engine Dyno 2.0. This is the new design with all the upgrades that I just discussed. As you can see, the entire setup is now contained on one weldment. The left-hand side over here being the engine mounted to its own plate that's dual slotted, or it's working on a dual slot system. And what I mean by that is I've got these slots underneath that run vertical relative to the screen that's used for sprocket positioning. So you're able to slide the engine left and right, kind of get that sprocket positioned. And then I also have a set of slots for chain tensioning. So as I drag this part, you'll see that engine can slide around, tension the chain, bolt it down. And again, it's on the same weldment now, so the rigidity should be no problem as far as handling or as far as removing the issue that we saw in the first design. Now, the lever arm itself was flipped from the right hand over to the left hand side. This is just a packaging thing. I couldn't fit a reservoir right here, and I didn't want it that close to the chain anyways. So I was able to flip this over. Now it's pulling upwards, so I had to flip that load cell upside down. And then I added this little retaining safety feature. In the event that the load cell fails, it doesn't just slap over to the other side of the table. As exciting as that would be, I don't want that to happen. So that's sitting there now and safely secure. Covering the load system itself, it's the exact same design as the first time, or at least it's a really close or similar design as the first one. There are 3 bearings, the shaft passes through all 3 bearings, and the pump itself is on a rotating mount, and it transmits the torque to the lever arm, just like the first design. The rotary encoder is no longer just kind of zip tied and taped to a piece of tubing. I've got a couple pieces of plate that hold up a 3D printed flat part that rotary encoder is going to mount to. And it has slots for some adjustability and flexibility as well. So that's what holds that in place. On the left-hand side now of the dyno setup is the hydraulic reservoir and the valve control stuff. So this is a 3-gallon hydraulic tank. It's a purchased component. Pretty straightforward. The filter bolts directly to it, so I kind of eliminated a hydraulic hose if I need to come to hose to filter. The hose layout is the same as it was before. You can kind of see all the connections now. And I have down here is my flow control valve. So the needle valve is mounted to this weldment over here. I've got a pressure gauge that's actually watching the pressure, so you can keep an eye on things. And then this feature up here that's passing through the handle of the flow control valve is my automated load control, or at least that's what I'm calling it. This is a planetary gear stepper motor mounted to a mount, and once you take the handle off of that needle valve, you'll be able to connect this stepper motor directly to the needle flow valve so that you can control the load on the system automatically in your control system. So I'll get to more on that later, but this is the design. Oh, and finally, almost forgot, it's on caster wheels. So that makes it a lot nicer, can kind of roll it around. And if I don't like the vibrations or I want to kind of isolate it a bit more, I can swap these caster wheels out for actual vibration isolating mounts, which will be pretty nice as well as far as options go. So in a nutshell, that's basically it. That's the version 2.0 of the Dyno. All right, with the design being wrapped up, that's enough talk. Let's bump some different music and get into the fabrication. Let's go. Let's take a quick break from the build and talk about how you can build your own small engine dyno exactly like this one. So what I've done is I've gone in and not only did I update the design to make it way more easier to put together, self-contained, store, align, test, tune, all those parameters. Not only did I make it more efficient in that regard, but I also have very, very detailed plans to put this thing together. So I'm gonna splash some images up on the screen here. Assembly prints, I have parts lists, sourcing information, I have DXFs and PDFs for all the plate cut steel. I have machining tolerances on everything that's required. I have the program code for the manual control valve. I have the program code for the automatic control valve. I have everything there ready to go to replicate your own and start creating your own dyno. With all that being said, it was a lot of time invested. It was a lot of energy that was spent into preparing these documents so that somebody else can read and interpret and kind of jump into this project on their own. And the way I felt best about releasing that to people is through a purchase on Etsy, selling these digital files ready for you to download and build your own. I spent a long time wondering if I should actually sell it or not, but ultimately I think it'd be a great win-win. The people that are interested in building something like this can jump into it at a relatively low cost, and the channel gets to grow. All those funds are gonna go right back into any kind of necessary tools, equipment, devices of any way, shape, or form to accomplish what I'm trying to do here. It's not going to make the channel or break the channel, but it is going to absolutely assist things in moving forward. Feel free to look in the description below. There's going to be a link there. If you're interested, check it out. If not, that's cool. Let's get back to the build. it has been a few days since I last turned on the camera, but I was able to finish all the welding on the main structure as well as paint it. Before I painted it, I wanted to ensure that my hoses were all the correct length based on the CAD model. So I did some sub-assembly work off camera. I got my hydraulic tank assembled as far as the fittings go. Same thing with the filter, same thing with the valve setup, and also the pump as well. Everything checked out, I broke it back down, got it all painted, and so we're ready for final assembly. Most of these components came off the original dyno design, so really it's just putting it back together and get everything hooked up. So let's get into it. Okay, so that's gonna wrap up the assembly work. We still have the electrical system to get to really quick here, but no real issues with it. Of course, with any kind of shaft, there's alignment, things like that. The shaft set screws and then the shaft actually clamping down onto the pump, that has to be spaced correctly so that it engages with the rotary encoder just fine. But besides that, there's really not a whole lot of fine tuning. I was able to greatly reduce the chain length. I already put away the section I took out off of it, but it was almost by half. So that's a significant improvement. And the base plate of the motor itself, being able to kind of shift it forward, back to tension the chain and then side to side help align it, was perfect. That did great. So let's kind of go through it in a little bit more detail. Okay, so just like last time, we have our pump mounted on a big bearing that's tightened down to our torque arm. Now the torque arm, as you can see, it's got plenty of play. And what I'm going to do is I'm going to zip tie it. I don't know if you can see it. It's got a hole in it down in there. I'm going to zip tie to this to kind of take up that dead space, but the zip tie being held to it is not going to affect what force it takes to rotate this pump from the motor. So it's not going to throw off the data measurement at all. It's just something I'm going to do to remove any kind of play out of it so that it's kind of already in a position where it's going to hold up against the load cell to start with. Again, the base plate of the motor did a great job getting us exactly aligned. We did a lot of chain length reduction. The chain is tensioned, or I can do a little bit more tensioning. The bottom side went a little slack, but it's got plenty of room left on the slots to kind of tension it up further. The load cell and my little safety restraint, oh, almost lost it right there. The load cell and my safety restraint lined out perfectly. You can kind of see that torque arm contacts that load cell before it hits that safety hoop. So we're good there. The casters are a welcome addition. Let's see, the rotary encoder. I don't know if I talked about why I needed 3D print this. I wanted a little bit more flex in this to kind of catch any kind of misalignment that might happen in the course of getting the rotary encoder attached. I have my filter. It's basically held in place by these fittings. That's done a great job. There's not a whole lot of load there, and I have plenty of room to access it, take it off, and change out that filter if needed. Let's see, back over here. Oh, let me cover this. This right here, these two zip tie holes, this is for any kind of wire strain relief. So I can go ahead and run a zip tie down there and kind of build up a little bit of slack. The rotary encoder has one as well, right down there. So that'll be good to go as well. The valve, this is probably my favorite part of this design. The previous design valve did not have any kind of really mount to it, but these valves don't have a mount structure that is easy to use. So what I do is I have this backing plate that clamps it down into place. That worked out great. It looks pretty slick. And then I have quick access for my pressure gauge as well. And then I just have that return line back to the hydraulic tank, which this tank is a really nice quality tank. It's 3 gallons, and it's not too expensive. So all in all, everything worked out pretty well. So we have to get the electrical stuff wired up. Then what we're gonna do is a test with the manual control setup using this valve, followed by putting on the automatic load control, which is done with this. So what's gonna happen is this piece of plate picks up these 2 holes, this handle comes off, and then this piece, which is the actual motor mount, attaches to those 2 holes on there, like so. And then I have a shaft coupler here, there, which is going to couple the motor shaft to the shaft of this valve. That way it'll give me my automatic load control. So let's get to some wiring, get the manual control system set up, fed to an Arduino, and then we'll do a test. Okay, everything is assembled. We are just about ready to go. The hydraulic tank has been topped off, and I tried my best not to make a mess, but it happened anyway, so there's that. I got my cable routing done. I've got the rotary encoder mounted back here, the load cell mounted right there. I use my strain release there for the zip tie points. And then I have the Arduino and its data acquisition kind of set up down here. I also have this geared down stepper motor, which is going to be for the automatic load control, but we'll get to that in a little bit. I just had it wired up anyhow to get going. So on this first run, what we're going to do, engine's going to get up to full speed. I'm going to start closing the valve manually. And what we're going to do is we're going to watch the load pick up. I'm going to take it, we're going to wind it down, see how much power we get before we start dropping RPM too much, and kind of test the manual setup. Now, we've done this before. The idea was to kind of get it much more refined, cleaned up, which it is, but I want to prove out to make sure it works just as it should. One more thing I wanted to quickly note is that I went ahead and added a 4th data set or data point to the column of information. The first one is going to be engine RPM. The second one is shaft RPM. The third one is the load that the load cell is picking up. And then the fourth one is the calculated horsepower off of the RPM of the pump shaft, and then the load on the load cell. I added engine RPM, which is different than shaft RPM, because I have a 12-tooth sprocket on the engine and I have a 24-tooth sprocket on the pump shaft to slow things down here as opposed to here. So I've got my throttle position, which should give me around 3,300 RPM or so. And we're gonna go ahead and apply the load from that point moving forward, instead of cranking the throttle all the way open, because I think it'll hang it past the governor, and then we'll just reach a natural RPM max when we hit valve flow. So instead of doing all of that, I've got the RPM positioned, or should be positioned just right. So let me get my safety gear on, get it fired up, and now we're actually gonna do the test. Okay, so normally I'd put up a graph of the data. Arduino 2.0 has effectively kind of killed the copy paste feature or the export feature easily out of the serial monitor port. There's ways around it, but I'll just put up some stills of the actual view or of the power run you just saw to kind of talk through it. But basically, we got the engine up to 3,000 RPM or so. You can see the graph kind of climbing. It gets to the point where it stabilizes at 3,000 RPM or 3,300. I actually uncheck it, and then I go check our horsepower calculation. Instantly, it's at 1, which tells me we had about 1 horsepower loss of parasitic drag, just the engine moving the pump in general, operating at that RPM, and just the backflow of well, the hydraulics itself. Then as I started to close the valve, you can actually see torque starting to rise. At some point, we pass the threshold of of the amount of torque that the engine can put out at its maximum engine RPM. So that causes the RPM to start dropping. And so it drops continually. Right around 2,500 RPM, we got roughly 17, 18 foot-pounds of torque. The manufacturer rates this engine at 2,500 RPM and 8.1 foot-pounds of torque, I believe. But remember, we have that sprocket correlation, so we have some gearing in there we have to account for. So the engine is actually making half of what we saw on the actual sensor. So it actually lines up pretty well. It's a lot healthier than I thought it was with the carburetor as it was sitting. So at this point, we're gonna stop using the manual load control feature. I'm gonna pull this handle off, install our servo motor, or stepper motor rather, and I'm going to employ the first kind of stepping stone into automated load control. And we'll talk about what my goals are right when we kick that off. So let's get to installing that motor. A lot of excitement in the air right now. I got my stepper motor hooked up to my flow control valve. So now the stepper motor is actually controlling, or will control, the flow control valve. I found one thing that actually needed a little modification to make it work, which was this piece of plate right here. It was a little bit too tall. I didn't have a good idea of how much my coupler could bite onto to interface with the flow control valve as opposed to the stepper motor. So I actually made it too high, or accidentally made it too high. I cut it down to length, no big deal, 3/8 shorter, move the bolt holes, move the top of the plate down. It's good to go, we're ready to go there. Mounts up the motor, no problem. And now the motor and the flow control valve are coupled together. So I then sat down at the laptop and I tried to come up with a control scheme that is kind of the first step into automatic load control. For a lot of steady state tuning functions, what you want to do is you want to hold a constant RPM. So what I'm targeting right now is 1800 RPM out of the engine. If it sees more RPM than 1800, it's going to start closing this down until the engine slows down to 1800 RPM. If it sees less than 1800 RPM, it should open back up. So I haven't actually tested this. I had the code turn the motor sitting here on the table. I didn't do any tests. I was excited. I just want to give it a shot, see what happens, and then catch it on camera. Worst case scenario, it just keeps on going and going and going until it closes this up, or I don't know, it'll eventually stop the motor, but the fastest way to stop it is just pull the plug out of the USB port. Now when I release this product, this is the code that's going to be paired with so that somebody can use this for steady state tuning, pick an RPM value, target that, and the load control will kind of hover in that area. The most advanced version of this is a really spec'd out load control system that will start at idle, and then if I control throttle to give it full throttle, it'll lock in that RPM and allow the engine RPM to climb incrementally what you'd expect to get from a large vehicle dyno or like a regular sized dyno for a car when they do a power run or a dynamic kind of tuning session. You get on the throttle, RPMs climb, but the dyno controls the speed at which those RPMs climb to peak RPM. And so it's a way more of an advanced controls problem. The reason I'm not going to develop that and then send it to people in a code is that coding is one of those things that you have to do it on your own to kind of get an idea of how it works, to then fix it, troubleshoot it if you want to use different components, a different controller, different control methods. Right now I'm not using any kind of PID or anything like that. If you wanted to implement that though, with the stepper motor it'd be a little bit tricky, but if you did want to implement it, you could do that. And so the coding side of this project is fairly open-ended. I'm just giving a rough start, and I'm sure people are going to find better ways to code what I have here, more efficient ways to grab the data, so on and so forth. So with all that being said, let's get to the initial test to see if this thing should work. Now, what should happen, I'll start up the engine, it'll go back to that 3,000 RPM or whatever it was operating at earlier today. The stepper motor will start to close the system because it wants to bring it down to 1,800 RPM. Once it does that, if it successfully takes it down to 1,800 RPM and plateaus, what I'm going to do then is I'm going to come over here and I'm going to reduce throttle, basically taking the power away from the engine, and it should dip below 1,800 RPM, and then the stepper motor should then open up the flow control valve. If we can do that, that's a huge success, and we're calling it quits with this project. But to capture what the flow control valve is actually doing, I've got a GoPro back there, so I'm going to catch the GoPro, I'm going to fire the graph up on the screen of, this time I'm going to show engine RPM, and that should be it. Let's get to it. Okay, so one other thing to add. Once I plug in the stepper motor requires 5-volt power from the control board to then read direction, kind of the discrete or digital values that set some parameters there, but it also needs a bigger power source. So I have a 12-volt power supply that feeds the stepper motor over there. So once I get these cameras rolling and start up the engine, the last thing I'm going to do is plug in that stepper motor so we can kind of together watch what it does. Okay, I already noticed it was going the wrong direction. So let's update the code, just keep everything rolling. Starting to build pressure. It worked. Almost the first try. I had my directions backwards when I first fired up, but that was awesome. Wow. Okay, so just like expected, everything's still recording. I'll just let it finish recording. Just as expected, the RPM, it took it a while to get there, but it dropped the engine RPMs down. It stagnated around that 1,800 RPM. I went over here, started closing the throttle, and then it reduced the load so that it kind of climbed back up to 1,800 RPM. Perfect. It could not have gone any better. That is awesome. That was a really fun project. I may have mentioned all of this before, but I wanted to fix the things that I knew could be so much better for a small engine dyno, just like this one. I wanted to be able to store it properly, and I wanted to make it better so that I could share it with people. If you're interested, you want something of your own that you can build, that you can work on, that you can make, feel free to check that out. And if not, that's fine. But as always, thank you so much for watching. This has been a lot of fun. And stick around because there's tons and tons more content coming out soon. Thanks for watching. Move into discussing? Let's just redo all of it. Try again. God. My ankle. Okay. That hurt. Okay.